Right now, beyond Neptune's orbit, dozens of space rocks are moving in patterns that defy explanation unless an unseen massive planet is controlling them. These trans-Neptunian objects orbit with surprising alignment, suggesting something substantial is influencing their paths. This represents the compelling scientific case for Planet 9, a world 5 to 10 times more massive than Earth hiding in the outer solar system. The mathematics suggests it exists, but finding it has become astronomy's greatest treasure hunt, like searching for a ghost ship in the cosmic ocean that leaves only ripples as evidence. This orbital puzzle has astronomers scanning the skies, piecing together clues of what could be our solar system's most elusive member. The orbital puzzle. What if the map of our solar system is missing its most massive piece? A piece so significant that it fundamentally changes our understanding of our cosmic neighborhood? This isn't a hypothetical question. It's a serious scientific possibility based on mathematical evidence and strange orbital patterns observed at the edge of our solar system. When astronomers look beyond Neptune, they find a population of frozen worlds called trans-Neptunian objects, or TNOs. These are essentially icy bodies orbiting the sun at extreme distances, much farther out than the 8 recognized planets. The Kuiper Belt, which begins just beyond Neptune at about 30 astronomical units from the sun. $1 Australian is the Earth-Sun distance, contains thousands of these objects. Based on our understanding of how solar systems form, these TNOs should orbit the sun with random orientations. Their orbital paths should point all different directions, like spokes on a wheel when viewed from above, similar to how the numbers on a clock face extend in all directions. But that's not what astronomers found. In 2014, astronomers Chad Trujillo and Scott Shepard noticed something strange. The most distant TNOs, those wandering far beyond Neptune's gravitational influence, weren't behaving as expected. Instead of random orbital orientations, these objects showed a peculiar clustering. Their orbits were aligned in a way that shouldn't happen by chance. The perihelions of these distant objects were clustered together in space, and their orbital planes were tilted in similar ways. This observation became even more significant when astronomers Konstantin Batygin and Mike Brown at Caltech analyzed additional objects and confirmed this pattern in 2016. They found that TNOs with orbits longer than 4,000 years showed this strange alignment. The odds of this happening randomly? Less than 0.007%. In other words, this clustering pattern would occur by chance only once in about 14,000 solar systems. Take the strange case of Sedna, one of the largest known TNOs. Discovered in 2003, Sedna follows an extremely elongated orbit that takes it from about 76 Australian dollars at its closest approach to the sun out to nearly 1,000 Australian dollars at its farthest, well beyond the Kuiper Belt. Objects like 2012 VP13, nicknamed Biden, follow similarly unusual paths. These discoveries provided crucial early evidence in a pattern that Batygin and Brown would later analyze in detail. What makes these alignments particularly puzzling is that these objects never come close enough to Neptune to be influenced by its gravity. They're too distant to be explained by any known planet's gravitational pull. Yet something is organizing them, something massive enough to herd these distant worlds into similar orbital patterns over billions of years. Here's what the data show. These distant TNOs have orbits that are both physically clustered and oriented in similar directions. When astronomers plot the orbital parameters, they find that the arguments of perihelion cluster around 0 degrees. The longitudes of perihelion also cluster together rather than being randomly distributed around 360 degrees as expected. Furthermore, these objects share another strange characteristic. They all have highly inclined orbits that tilt in the same direction. This is particularly strange since objects so far apart shouldn't know about each other's orbital orientations. It would be like finding that cars in different cities across the country were all parked at the same angle. There must be some reason for such coordination. When astronomers create simulations comparing the expected distribution versus what's actually observed, the contrast is striking. What we see is a distinct clumping in particular regions of space, as if these distant objects are being shepherded by an unseen force. What could possibly be organizing these distant worlds? The mathematical answer that emerged, a massive planet, much larger than Earth but smaller than Neptune, orbiting the sun at an extreme distance in the outer solar system. This hypothetical planet would need to be on an elongated orbit inclined to the plane of the solar system to create the observed patterns. Its gravity would gradually shepherd these smaller objects into their aligned orbits over billions of years. The statistical significance of this clustering, 3.8 sigma, indicates it's highly unlikely to be coincidental, compelling enough for serious scientific investigation, though not yet meeting the gold standard discovery. With this compelling orbital evidence, astronomers began developing a hypothesis to explain this cosmic mystery. They started running computer simulations to determine what kind of planet could create these exact orbital patterns, testing different masses, distances, and orbital characteristics. Through mathematical modeling, researchers at Caltech determined that a planet about 5 to 10 times Earth's mass on an orbit tilts about 30 degrees to the plane of TNO clustering. This planet would take between 10,000 to 20,000 years to complete a single orbit around the Sun. The simulations showed that over billions of years, this planet's gravity would gradually force TNOs into the exact orbital patterns we observe today. The orbital puzzle of these distant objects had yielded an extraordinary possibility. Our solar system might contain a ninth major planet that has escaped detection until now. But how could astronomers prove the existence of a planet they couldn't directly see? The answer lay in the same approach that led to Neptune's discovery in the 19th century, through its gravitational effects on other objects. The hunt for Planet 9 had begun, using invisible influence as the primary clue to its existence. Invisible influence? How do you prove something exists when you can't see it? This isn't just a philosophical question, it's a practical challenge that astronomers face when searching for objects at the edges of our solar system. For Planet 9, the evidence doesn't come from direct images, but from the invisible pull it exerts on other bodies. This approach has a long and successful history in astronomy. When we look at those clustered TNO orbits, they tell us something profound. A massive gravitational influence is shaping them. Despite extensive searches of the outer solar system, telescopes haven't captured any images of a large planet that could be responsible. This invisible influence presents both a puzzle and an opportunity. By studying the affected orbits of smaller objects, astronomers can mathematically reconstruct what remains hidden from view. Detection through gravitational effects rather than direct observation has proven reliable in astronomy's history. In 1846, astronomers noticed Uranus wasn't following its expected orbit due to an unknown gravitational pull. Two mathematicians, Urbain Le Verrier and John Couch Adams, independently calculated where this unknown planet would need to be. Their mathematical predictions led directly to Neptune's discovery, pinpointing a world that had remained invisible until calculations revealed exactly where to look. Today, this same mathematical approach drives the Planet 9 investigation. When Konstantin Batygin and Mike Brown examined distant trans-Neptunian objects, they discovered something statistically improbable. The 6 most distant known objects all followed elliptical orbits pointing in the same direction in physical space. The odds against this happening randomly were overwhelming. Something had to be organizing these orbits, and the most plausible explanation was the gravitational pull of a substantial unseen object. Initial calculations suggested this object would need to be quite massive, a true planet with several times Earth's mass. Smaller objects simply wouldn't exert enough gravitational force to shepherd these distant worlds into their observed patterns. To test this hypothesis, astronomers employed powerful computer simulations that function like virtual solar systems. These tools allowed researchers to introduce different types of planets and observe how their gravity affects smaller objects over billions of years. By comparing simulation results with actual observations, they could determine which scenario best matched reality. After testing numerous configurations with planets of different masses and orbits, a specific solution emerged. The data pointed to a planet with 5 to 10 times Earth's mass, orbiting at an average distance of 500 to 600 times the Earth-Sun distance. This orbit would be highly elliptical, taking the planet between about 200 and 1,200 astronomical units from the Sun. Crucially, the planet would follow an anti-aligned orbit, its closest approach to the Sun occurring 180 degrees across from the perihelions of the aligned TNOs. This anti-aligned orbit is central to the Planet 9 hypothesis. Simulations showed this configuration prevents smaller TNOs from colliding with the massive planet while keeping them aligned through mean motion resonance, similar to how Neptune maintains Pluto in a stable orbit, though operating over much greater distances. The simulations revealed Planet 9 would naturally produce objects like Sedna by gradually pulling standard Kuiper Belt objects into more extreme orbits less influenced by Neptune. This explained puzzling discoveries of objects with highly elliptical orbits too distant to be affected by Neptune's gravity. What makes these mathematical models compelling is their consistency. Simulations of a solar system without Planet 9 strongly contradicted the observed data. The probability that the observed clustering was merely coincidental was calculated to be less than 1/100%. As Badigan and Brown noted, a solar system without the hidden planet is strongly refuted by the data. The model also predicted additional effects that have since been confirmed. For instance, it predicted objects with orbits perpendicular to the plane of the solar system, and such objects have indeed been discovered since the hypothesis was first published. Each matching discovery strengthens the mathematical case. These calculations provide astronomers with search parameters. Based on the predicted orbit and mass, they can estimate Planet 9's brightness, sky motion, and likely position. While these estimates cover a substantial area of sky, they significantly narrow the search compared to blindly scanning the entire outer solar system. The proposed mass of 5 to 10 times Earth's would make Planet 9 the 5th largest planet in our system, smaller than gas giants but substantially larger than Earth. This size plays in the category of super-Earths or mini-Neptunes, a common planet type found around other stars but absent in our solar system until now, perhaps. The math suggests this missing planet would reshape our understanding of the solar system's architecture. While mathematics can't reveal everything about this world, it provides a framework for what telescopes should seek in their ongoing search for our solar system's most elusive member. The Cosmic Detective Story. What are these space rocks telling us that we've missed for centuries? Throughout the outer solar system, a group of unusual objects are silently providing evidence that could rewrite our understanding of planetary science. These distant trans-Neptunian objects serve as silent witnesses in our cosmic detective story, celestial bodies with particular orbital characteristics that challenge our current model of the solar system. They communicate through their paths, telling a coherent story despite being separated by billions of miles. The key testimony begins with Sedna, discovered in 2003. This planetoid follows an extremely elongated orbit, traveling from about 76 astronomical units at its closest approach to the Sun, perihelion, to an astonishing 1,000 Australian dollars at its most distant point, aphelion. For perspective, Earth orbits at 1 Australian dollars, while Neptune orbits at about 30 Australian dollars. Sedna's journey around the Sun takes approximately 11,400 years to complete. Sedna's orbit reveals something extraordinary. It never comes close enough to Neptune to be influenced by the ice giant's gravity. While most objects in the outer solar system have their orbits shaped by Neptune's gravitational pull, Sedna exists in a detached state, seemingly beyond the influence of known planets. The plot thickened in 2012 when astronomers discovered another object with remarkably similar characteristics. Designated 2012 VP-113, nicknamed Biden, this object's closest approach to the Sun occurs at about 80 Australian dollars, even more distant than Sedna, and it too remains beyond Neptune's gravitational reach. Both objects inhabit what scientists consider a dead zone, where the known planets exert minimal gravitational influence. Their elongated orbits carry them far beyond Neptune, with the majority of their journey spent in the distant frigid regions where our solar system transitions to interstellar space. As astronomers identified more distant objects, a compelling pattern emerged. Objects like 2015 TG-387, nicknamed the Goblin, and 2015 BP-519 displayed orbital characteristics aligning with Sedna, and 2012 VP-113. These extreme TNOs share detached, highly elliptical orbits with suspicious similarities, like multiple witnesses independently corroborating the same account. The most revealing aspect of these orbits is their clustering. When mapped, their elliptical paths point in the same direction in physical space. Their perihelions, closest approaches to the Sun, occur in the same region rather than being randomly distributed. This alignment sparks wonder among astronomers. It's as though these mute cosmic travelers are collectively pointing towards something unseen. Even more telling, these objects' orbits tilt approximately 30 degrees downward in the same direction relative to the plane of the 8 known planets. Calculations place the probability of this alignment occurring randomly at about 0.007%, virtually ruling out coincidence. The clustering extends to the argument of perihelion, a technical parameter describing where an object's orbit makes its closest solar approach. For these distant objects, these values cluster around 0 degrees, another pattern that shouldn't occur by chance. Orbital resonance might explain some outer solar system objects, but these extreme TNOs don't match known resonance patterns with Neptune or any other known planet. While Pluto orbits the Sun exactly 3 times for every 2 Neptune orbits, creating a stable relationship, Sedna and its companions show no such resonances with any known planet. Observing these objects over thousands of years would reveal them tracing massive elongated paths, never approaching Neptune or other giants. Yet somehow these widely separated objects share orbital characteristics suggesting a common influence, a shared storyteller affecting their cosmic journeys. The mathematical improbability of this happening randomly about 1 in 100 has compelled astronomers to consider alternative explanations. These TNOs function like buoys in the cosmic ocean, aligned by an underwater current, responding to an unseen force organizing their movements. The most plausible explanation is the gravitational pull of a substantial planet-sized world at the system's edge. Over billions of years, this planet's gravity would gradually shape the orbits of smaller passing objects, herding them into similar patterns. While glacially slow by human standards, this process works perfectly on astronomical timescales. The trans-Neptunian objects reveal a significant gap in our understanding, suggesting a massive planet shepherds their movements from beyond our current observational reach. The patterns in their orbits represent fingerprints left by an invisible hand, one belonging to a planet we've yet to directly observe. Based on its gravitational effects, astronomers can estimate this potential Planet 9's likely size, mass, and composition, painting a picture of a substantial world that would reshape our understanding of the solar system's architecture.